Hello everyone, welcome to Technologies Discussion channel. Today, I'd like to continue the discussion on filter design. Okay, so for this video, I'm going to discuss how can we actually design and develop a low-pass filter on a microstrip line. So basically, this will be the objective of this video. On my first part of the video discussion, okay, I will discuss how can we actually implement a low-pass filter using lump element like L and C, inductor and capacitor. Next, okay, I will make use of Richard transformation to transform the lump element into transmission line. After that, I'm going to make use another so-called rules, okay, Kuroda identity. Okay, so the key purpose of Kuroda identity is to convert the series transmission line into shunt transmission line so that it can be easily implemented on microstrip line. So basically, all this will be the objective of this video. From the lump element, after that convert to microstrip line, and therefore we have a low pass filter on microstrip line. This will be the part 17 series discussion on filter design. So guys, if you're keen to know more about filter design, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on filter design. This is my email. If you have any question regards on this discussion, okay, please drop me an email. Okay, or if not, if you want to have a faster response, you are always welcome to ask me your question through the comment. Before I continue, I'd like to urge you guys to help this channel by like this video. When more you guys actually help to like this video will have a better chances to reach up to a larger audience. So guys, help me press the like button now. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for some support. On this diagram here, it actually shows the frequency response of a low pass filter. From this diagram, you can see that all the signal under low frequency will be allowed to pass, while all the signal under the high frequency will be antennated away and will be removed away. Let's take a look on this L session network filter. On the left will be the filter input. On the right will be the output of the filter. So under the pass band, the input signal, okay, at the input supposed to be able to arrive at the output of the filter. While under the stop band, the signal at the input of the filter will not be able to arrive at the output of the filter. So how can we actually do this? Okay, so this is the LC network. Okay, whether the series supposed to be L or C, I will explain this. Whether the shunt supposed to be C or L, again, I will explain this. Let's start by understanding the reactance. Okay, so the reactance of the inductor is governed by this equation, and the reactance of the capacitor, which is governed by this equation here. I'd like to break into two parts for discussion. Okay, under low frequency and also under the high frequency. Let's start under the low frequency first. Okay, so under the low frequency, okay, for example, this frequency will be very small. So whatever the number that actually multiply, the reactance will be a very small number. So let's just quantify as 0.1 ohm, okay, for easy, okay, understanding and illustration. So basically, when the frequency is small, the reactance of the inductor will be very small. Okay, let's take a look on the reactance on the capacitor here. Okay, so basically this frequency will be very small. 1 over very small number, this will become a very big number. So again, let me just assume 1000 ohm, okay, to make the discussion easier. Okay, so now let's take a look. Okay, for example, the signal appeared at the input of the filter. Okay, so basically this signal is low frequency. So you can see that this actually offer a reactance of 0.1 ohm. So you can see that the signal will be able to pass from the input to the output. The signal will not be so-called reluctant. They are actually very reluctant to follow this path, as this path actually offer a high reactance. So basically, from here you can see that under the signal that is classified under low frequency, they will be able to pass from the input of the filter to the output of the filter. So basically, this is actually the characteristics of low pass filter. Next, let's move on to the high frequency. Okay, so the high frequency, it will be slightly different now. So the frequency here become high, so you can assume that the reactance of the inductor will become a very big number. Again, let's just assume 1000 ohm. While over here, the frequency become very high, and 1 over a very high number, this number will become a very small number. Again, let me just denote this 0.1 ohm as the reactance of the capacitor. So now, this is under high frequency. The signal, okay, which is high frequency, appeared at the input of the filter. Okay, now you can see that they actually offer a very high so-called impedance over here. The signal will be very reluctant to travel this path. But over here, you can see that the reactance is actually very small. Okay, so therefore the impedance is small. So basically for the signal at the high frequency, they will travel this path, which is so-called grounded to the ground. So from here, you can see that when the signal having a low frequency, they will be allowed to pass from the input of the filter to the output of the filter. However, when the signal having a high frequency, instead of passing from the input of the filter to the output of a filter, they actually shunt all the way to the ground. So basically, this is the characteristics of low pass filter. Okay, so with this, I think you have a better understand in terms of the design using lump element. Okay, so let's kickstart the discussion here. Okay, so again, okay, if you still remember, this is what is required to point. Okay, so basically, whether the L supposed to be on the right or supposed to be on the left. Okay, if you still remember, for this case here, it's look like a gun. Okay, so imagine that the impedance. Okay, the gun is always point to the smaller impedance. Let's say the load having a smaller impedance than the source, then you can configure in this way. Okay, if not, let's say the source, okay, having a so-called smaller impedance as compared to the load, then this L need to be shipped in this branch here. Again, if it's not sure, okay, please see my part 5 series discussion in order to fully understand this. Okay, but let's not dwell so much on this. But I hope you can understand the rationale. Okay, why L supposed to be in series and C supposed to be shunt in order to achieve a low pass filter. Let's continue. Okay, with this, okay, so let's come to the example here. Okay, so the example tasks us to design a low pass filter using microstrip line with specification as following, okay, which is the third order, okay, which means that I need to have three lump element n equals to 3, having the cutoff frequency of 4 gigahertz and using 3 dB equal ripple characteristics, which means Chebyshev. Okay, so how can we actually do this? Okay, firstly, okay, we are given the information, okay, the number of order of the filter, which is 3. So therefore, I know that I need to have 3 so-called L and C. Okay, so basically, I need to have 3 element of lump element. Okay, so this capacitor, whether is it on the left or whether is it on the right, it doesn't matter. Okay, but most important case, the series must be a inductor and shunt must be the capacitor, which I have just explained earlier on. Okay, so basically this is the G1, G2, and G3 value here. Okay, so since we are given a task to design at 3 dB equal ripple, okay, we can always look at the lookup table here. Okay, so this is the lookup table for 3 dB ripple here. So from here, you can see that G1 is 3.3487. Okay, as you can see from here. G2 will be 0.7117. Okay, so G3 will be 3.3487. Okay, G4, okay, basically, if it's odd, okay, then it will be symmetric. Okay, but over here, just make the whole thing so-called complete, and I just denote G4 as equals to 1. Okay, so once we have this, we are ready to design. Okay, so these are all the value that I actually obtained from the table here. Okay, I don't want to do any changes. I just put the number over here. Okay, so this is the G1 value here. This is the G2 value, 0.7117. This is the G3 value. Okay, so this is the 4, which is 1. Okay, so I'm not going to discuss this further on the load side here, but I just mainly want to concentrate on these three lump element over here. Okay, so this value are simply obtained from the table. Okay, let's say if you want to use 3 dB ripple, then you copy the 3 dB ripple. Let's say if you want to have 0.1 dB ripple, again you just copy whatever value on the table and then you just put into the component over here. Okay, so this is the first task. Okay, so once you have do this, okay, again, okay, like I mentioned earlier on, I'm going to make use of this Richard transformation. Okay, so the key purpose of Richard transformation is to convert the lump element, inductor and capacitor to series and shunt stub here. Okay, so the characteristics impedance of a series, okay, which is for inductor, and the characteristic impedance of a shunt stub, which is for capacitor. In short, okay, so if you have a lump element of L, okay, so basically they look like this. You has a series so-called stub. Okay, remember the length of the transmission line will be lambda over 8. This thing will fix. Okay, nothing will be changed. Okay, so in order to use this Richard transformation, okay, the wavelength, okay, of the transmission line will be lambda over 8. And if it's a inductor, then it will be a short circuit. While let's say, okay, it's a capacitor, okay, the length of the transmission line will be still the same, okay, but it will be a open circuit. Okay, one thing I want to highlight also, you can see that this is 1 over Z naught equals to Z naught. While this case, they are exactly the same. This one, I need to do a 1 divide, okay, which I will further explain this later on. Okay, so basically, this is for Richard transformation. Okay, again, let's not dwell so much on the equation. Let's just understand how to use them. Okay, so once we have all these here, okay, so this is for the inductor. Okay, so these are for the capacitor. If you still remember, okay, basically I can replace them with a series stub, okay, for inductor. Okay, so this is also an inductor. I actually have a series stub here. Okay, so if you still remember for inductor, okay, it will be represented by a short circuit. So therefore, there will be a short circuit over here. Okay, so as for capacitor, okay, I will be represented by an open circuit. Okay, so basically you can see that this will be a shunt, so-called transmission line with an open circuit. How much will be the value? Okay, so basically the L will be remain the same. If you still remember the Richard transformation, okay, the L value will be the same, while for the C is reverse 1 over. So this is the same, this is the same, okay, but for capacitor, I need to do 1 over 0.7117, which give me 1.405. So over here, you can see that I make use of Richard transformation to convert the lump element into series and also shunt stub, as you can see from here. Okay, one thing I want to highlight again, remember the length of the transmission line, okay, to do this implementation on using Richard transformation, the length must be lambda over 8. Okay, keep this in mind. I will so-called remind you guys on this on my last few slides here. So this is actually after implement the Richard transformation. I have the so-called transmission line model now, and I'm ready to implement on microstrip line. However, before I can actually implement on microstrip line, it is always very challenging, okay, to represent the series shunt, okay, on a microstrip line. It will be very easy to so-called represent a open circuit, okay, shunt line. Okay, this series I may have some issue. So what I need to do is, okay, I will mention this, okay, but before I mention this, guys, again, this is very important to me. I urge you to help this channel by like this video. Again, for those who have learned something from this video, I appreciate that you can show me some form of support by subscribe to this channel and also turn on your notification bell. Once again, thank you so much. Let's come back to the discussion. Okay, so as I mentioned earlier on, this series sub may have some issue to implement on microstrip line. So I need to convert them into a shunt stub here. Okay, so what I need to do is I need to implement this Kuroda identity. Okay, so the key purpose of Kuroda identity is to add the unique element. Okay, so this is the unique element that I actually add over at the end of the filter here. Okay, let me explain here. when I actually add the unit element, okay, if the characteristics impedance of the transmission line is the same, okay, for the load, okay, you can imagine that nothing will be changed. All the signal will be able to propagate. No reflection actually occur because it's perfectly matched. Okay, so basically when I actually add the unit element, nothing changed on term of the characteristics of the filter. Okay, let's say when you probe over here or you probe over here, nothing changed. Okay, when you actually implement this unit element over here. This is what they want to say. The series stub will be very difficult to implement in microstrip line, okay, which is over here. So we use one of the Kuroda identity to convert this to shunt stub. Okay, we will be able to convert this series to shunt stub, which I'm going to show it to you shortly. Okay, so this redundant element do not affect the filter performance since they are matched to the source and load. Okay, so basically this is what I want to say earlier on. So once we have this, okay, we are ready to perform the Kuroda identity. Okay, so how to perform the Kuroda identity? Okay, so basically this is actually one of the Kuroda identity. Okay, so how can we actually know that this is the one? Okay, remember this is a inductor. So this is an inductor. So this is a unit element. The unit element is actually implement over here. So what we want to do is we basically convert them into this portion here, which is I managed to have a so-called shunt stub now with this case here. Okay, so the key purpose is to convert the series stub to shunt stub. So therefore, I need to do the calculation to find out what is N2Z1 and 1 over N2Z2 over here. But from this equation here, you can easily see that this portion is actually the Kuroda, like I mentioned earlier on. This part will be the Z1. This unit element will be the Z2. So from here, okay, I know that Z1 will be equals to 3.3487 and Z2 will be equals to 1. Okay, so once I have this, I can easily compute my N2 value, right? I have my Z2 value, which is 1. I have my Z1 value, which is 3.3487. So with that, okay, I can calculate my N2 value. Okay, so on my next slide, okay, so from here, again, I can calculate my N2 value, okay, with Z2, which is equals to 1, and my Z1 is 3.3487, if you still remember this. Okay, so basically, I will able to obtain my N2 value. Once I obtain my N2 value, I can find my N2Z1. Okay, so N2Z1, so Z1 is actually 3.3487 here. So I can so-called calculate, which is 4.35. Okay, so the next portion here, according to the Kuroda identity, is 1 over N squared Z2. Okay, so again, this is 1 over N2. Okay, so N2 is equals to 1.299. So 1.299 multiplied by Z2, okay, Z2 is equals to 1. And I will be able to obtain this number, okay, which is 0.767, which is shown over here. Okay, so basically I have successfully transformed the series stub into shunt stub, having totally different value, okay, as compared to just now. So with this, okay, I can start to redesign the transmission line. Okay, so this will be 4.35. Okay, so this is the portion that I told you that I'm going to modify. If you still remember, this is the capacitor side, which I'm not going to modify. This is the inductor side, which I need to replace with a shunt stub, right? Okay, so basically this 4.35 will be here. This part here, remember, because for capacitor, I need to do a 1 divide. So 1 divided by 0.767 will be equals to 1.299. Okay, so since the transmission line is symmetric, okay, so earlier on I have shown you to you just on the right hand side, but because I know that this transmission line will be symmetric, so therefore you can see that I can easily copy the value. So this is the capacitor. Okay, so I can easily copy the new so-called shunt stub as you can see from here. So this is actually the final low pass filter on a microstrip line. Okay, you can easily see that I actually just need to fulfill with the shunt transmission line rather than the series transmission line, which I have it earlier on. Okay, again, I like to highlight this. All the length, okay, will be lambda over 8. Okay, because you are going to make use of the Kuroda identity, so all the value need to be remain at lambda over 8. Okay, so once I have all this, okay, next I need to do is I just need to denormalize. Okay, because you can see from here, the resistor, okay, value is 1, and this resistor which is the source, is equals to 1. I need to transform them back to 50. How can I actually transform that back to 50? So all this number I need to multiply by 50. 1.299 multiplied by 450, I supposed to get this 64.9. Okay, so 4.35 multiplied by 50, okay, I supposed to get 217.5 ohm. So basically with this, I can easily implement this on a microstrip line. So this show you the diagram of a microstrip line layout. So this is the input, this is the output port. This is actually the input port. And all this basically is the characteristics from here, 64.9. Okay, this is the so-called the connecting line, 217.5. And this is from the capacitor, which is 70.3, etc. So basically with this, you can see that I firstly start out with the lump element, then I convert into so-called series and shunt transmission line. After that, I make use of Kuroda Identity, okay, to convert the series transmission line into shunt transmission line. And finally, I actually obtain the microstrip line layout as shown over here. So again, from here, if you run the simulation, okay, you can see that the distribution line is actually a bit over here, and there's another distribute portion here. There will be another passband over here. Let me explain why we have this. Okay, so the calculate amplitude response of this filter is plot alongside the response of the lump element version. So you can see that this is actually the lump element version. For the distributed, which is the transmission line, okay, basically is shown over here. Okay, note that the passband characteristics are very similar up to 4 gigahertz. So from here you can see that they are actually very similar up to 4 gigahertz. So whether you implement by distribute or by lump element, they have the same characteristics on the passband up to 4 gigahertz. Okay, but the distribute element filter exhibit a sharper cutoff. Okay, you can see that this distribute element has a so-called higher Q as compared to the lump element because they have a steeper skirt, as you can see from here. Okay, so basically this is what it means. Okay, additionally, okay, observe that the distribute element filter response repeat every 16 gigahertz. Okay, so earlier on I told you that this is actually at 4 gigahertz. So after so-called the 16 gigahertz, they actually repeat again. Okay, so this is because we make use of Richard transformation. When we actually make use of Richard transformation, they actually are repetitive, okay, or they have a period. Okay, so therefore we have another passband at the magnitude of the so-called the cutoff frequency again. Okay, so basically with this, I'd like to end my discussion. In this video, I have discussed firstly, how can we actually design the low pass filter using the convention, okay, L series, which is the lump element using the inductor and also the capacitor. Then I make use of Richard transformation and Kuroda identity to convert them so as to so-called implement the lump element design into microstrip design. With this, thank you so much for strong support. I hope to see you guys soon. Bye for now. Thank you so much.